I think my screen is visible, right?
Yes. Yes. Yes.
Okay. So today's presentation will be related to two new topics. One of them is a new topic. Earlier, the past one we might have seen, but I'll still start a revision on that topic. The one is PPO and the other one is DPO. These both come under the time when we start fine tuning our LLMs. I'll keep on introducing them and their working procedure as soon we pass in our presentation. So starting from what happens is nowadays LLMs are getting powerful day by day and they are improving their capability over the time. Uh, but there's a thing that we always do to improve their capabilities to further enhance their performance is we always do some kind of calculation over the loss to what they predict and what we actually want. This thing is always there. Uh, Traditionally, this is the most common function, the cross entropy. Over the time, as we progressed in NLP, there were two new things, loose score and rogue. They are other kind of again function to find a loss. They do it by finding whether two words, whatever the predicted word by LLM or and what is the reference words, how much they are overlapping or till what expect they are similar somehow. Uh, but again, simply compared to generated text, so they use some kind of again different rule depending on the which version of these matrices you are using. You are using ROG L or N or LCS, something like that. But still they can't achieve performance that we expect. So wouldn't it be great if we use directly, if I say, human feedback for telling RLM how good they are able to generate their text or not? I mean, that's the end goal we are expecting. So we can directly measure the performance on the go and even give them a feedback to let them optimize their performance over the time. This is the core idea behind reinforcement learning with the help of human feedback, which is known as RLHF. We use these methods from reinforcement learning, from machine learning era, where they were supervised and supervised, and there was then RLHF semi-supervised. So this is one of that technique, RL technique, reinforcement learning. But now, if we want to use with the language models, we'll use human feedback as the core pillar here to get their loss function more optimized and their performance boosted up. Coming to step, what are the steps in RLHF? How this RLHF comes into picture. Just a second, I'll adjust my screen. Okay. So there are four things that actually happens in RLHF. There is always a action which AI performs. In our case, it will be an LLM. So let's say if I start doing something, LLM. I have a LLM. Uh, Initially, we'll start with some kind of prompt here. If I say, how are you? There's some kind of like uh, first push which happens to these AIs, or in our case, this is LLM. There will be action for that first push we have gave. There will be action. Either it will be a good action or a bad action. If I say the action is, he says, our LLM outputs what? For sure, this is not a good action. This is kind of rude sentiment that our LLM is providing to us. So what we'll do is uh, we'll give a feedback. A human provide feedback to on a task what we asked our AI to do. We'll provide that this is a bad action. uh, what will happen is like with this feedback, our LLM will adjust its parameter, and it will learn like whatever action he has done now is not a good action, and he has to improve over the time. Again, what will happen is this cycle will repeat continuously till we are satisfied with what our LLM is doing or our AI is doing, uh, until a point it start performing well. So now what will happen is like if we start our cycle again with the same prompt, how are you? Now our LLM, instead of what if it says k good. Now in this case our feedback will be like sure. Now, in this case, our feedback will be like, "Oh, this is a good reply or the expected reply we want from our AI or from our LLM." So our feedback will be like, "This is a good thing," and will provide some kind of positive score. And by this, our LLM will learn that this is the thing that he has to ignore, and this is the thing with what he has to go with. So over the time for different tasks, we will keep on providing different kind of feedback to our LLM, and this is the basic cycle which is present in every RL application, reinforcement learning application, and here we just added a touch of human feedback as per our scenario. So cycle will start from some kind of action, from some kind of initial push. There will be some kind of action that our RL will perform, and over that will provide some kind of response, and then AI will learn over the time. So this is action, feedback, and learning. So these are the basic pillars of our RLHF. This is how the basic reinforcement learning works. I hope everyone is fine with this till now. Okay, so let's move to our first topic of today's presentation, which is a PPO. PPO directly doesn't comes into picture because it is a part of a large task itself, of a RLHF, which I just easily covered in 3-4 lines. That will keep on expanding over the time. Different components will be keep on adding into it. Uh, Starting like how we can start is we'll have some kind of initial model, uh, for like this will be our LLM here, or AI, whatever we want to say. uh, Secondary thing will be having human feedback for sure. This will work as our feedback. uh, Third thing which happens in RLHF in NLP, I'm talking about, is like we are going to train a reward model. Like now, your question will be like, why do you need a reward model? Like, what is this reward model, or what is happening? Like, where does this third thing comes into picture? The thing is like, over the time, what will happen is like annotating with the help of human is a expensive and time-taking task. You can't just keep on annotating with the human annotators. It will take a long time, and a lot of resources as well, because we can't annotate with that much speed. We can't just go and annotate each of the output which are LLM or AI will produce. So what we'll do is we'll create our own version, something like that. What uh, he, what that version or what that machine is gonna do is it will have a human persona in it. So it will provide a feedback now in place of human. Like if I say that I'll just take some space and withdraw. So what will happen is I have a LLM. It does some action. After action, human comes into picture and it gives feedback, which goes back to LLM. Uh, because because our human feedback is a expensive task, like we can't just use humans for every and easy task for a long period of time. What we'll do is we'll just take this thing out, and instead of this, I'll put some reward model which will behave like human. Now this thing comes into picture and this thing just goes out. So instead of human who is going to give feedback, now I have a reward model which will give feedback to all the actions what our AI is performing. So that's a use of a reward model. Then we have a thing like we got our reward model, we got our human, like human kind of feedback from that reward model. Now there will be a fine tuning which will happen with the help of PPO. Now, moving to more technical term, our LLM or AI, whatever I was calling till now, is known as a policy model. So from now onward, we'll say it's a policy model or a model which we are training or improving over the time. So this word now is now our LLM. So what we'll do is with the help of feedback that our reward model will give, will fine tune our policy model with the help of another thing which is known as PPO. I mean, you can't just directly feed in the reward into a model as per now and say that this is your reward, just do whatever you want to do. We need some kind of intermediate function to control that dosage of reward, whatever that policy model is getting, and how the loss function will be calculated. That thing will be done by PPO itself. So this is how our PPO comes into picture. Uh, there will be multiple further steps like how we do apply PPO and how we like once we do apply a PPO, we can do this iterative training. Again, the loop will be there. I'll create a small loop here somewhere just to illustrate what will happen now. What will happen is I have a policy model. I'll give some action. I have a reward model. It will provide some feedback. I have a PPO, the big box, which will suggest or as per now we'll take it as a suggestion, suggest the required changes. This is how this cycle is going to get complete. I hope everyone get an idea how PPUs come into a picture. I mean, if you can give thumbs up or something, or if you have some doubt, you can ask. Okay, so
Ankit, just one question here, right? So,
yes,
see,
sir.
why do we need a PPO kind of an optimization function? Why not we just use the output from the reward function and retrain the policy model?
Uh, there's a second thing also that will come into picture now, the reference model itself. So that also provides some kind of feedback which is required by PPO itself, so that our model which we are training doesn't drift away from the actual knowledge he has.
Okay, fine.
That's why we
Okay.
need DPO. I mean, that's the whole point why DPO occurs, to counter this question why we need DPO itself. I'll explain over the time. There's a thing now that is known as KL divergence. How that thing comes into picture is, I'll just take a second. We'll move to some free up space. I'll now keep on adding some elements into this cycle which we have studied till now. I'll just copy paste that cycle if it is possible. This will be our kind of mini map or reference to what we are doing. What happens in this RLHF, full-fledged RLHF now is I have a policy model for the learning model, which learn new things over the time. In parallel with that, I have a, again, if I say this policy model is a model S at this point, I have another replica of same model S, but I'll call it reference model, non-learning. There will be some kind of prompt here which will come. Prompt will go in both of these models. As per their capability and their learning, they'll produce some kind of output. This output from learning model or policy model will go into reward model. Uh, on basis of the performance, what policy model has done, or on basis of the action, it will squat out some score. I'll take that score and find out a KL divergence. I'll tell what KL divergence is. KL divergence, basically it just figure out how far the there's a difference between two text or the piece of text we have here. Coming to our context, it tells that what policy model has outputted is how much it is different from the original model whenever it was in past, the reference model or the duplicacy. Because over the time it will learn and it will keep on improving its capabilities, so the answer will become more polished now. But reference model will also give answer to the same model, same prompt which we have. So we'll find a KL divergence over both the output to find out how better or how far that policy model or learning model is out giving the answer compared to original reference model.
So Ankit, what do you exactly pass in the scale divergence function?
I'll explain the formula, sir.
Hmm.
First of all, I'll complete this circle itself. I'll explain the formula. Then we have a PPO, which will calculate a loss and if I just directly say a loss, because this is the core function of PPO itself. It will calculate a loss and help the learning model to adjust its parameters over the time. Our We started from this text, I think, where our core context was at that time. Okay, simply wouldn't it be great to use human feedback to for the generated test? Uh, because we want a better loss function so that our model can optimize more in more depth. Uh, here it is stated, use a method for reinforcement learning to directly optimize language model with the help of human feedback. Coming to this thing, now we have a reward model which is mimicking as a human feedback, and with the help of that we are calculating our loss. So this is how this complete cycle fit into that picture that I just shown you right now, in the text. Like, we are just using a human feedback, but we can't use human because human are expensive, so we are creating some same model with a human persona so that it can provide human feedback in place of humans, and with the help of that we'll calculate a loss. With I'll start explaining how this circle works. I have a prompt here. Let's say my prompt is will be next good PM. Will be next good candidate or good person as a prime minister. Let's say our model was trained with some previous data, and the original model, the reference model, says Rahul Gandhi, and a new model which is now somehow fine tuned, or over the time it has improved its capability, says Narendra Modi. With the help of this Narendra Modi, I'll provide some score with the help of my reward model. I'll provide some score like this is a good answer, and human do prefer as per Narendra Modi, or looking at the current trend, this will be the more of a preference for a human. It will provide some positive score. We'll find out some KL divergence, like whether my output is much is not in out of the context totally with the original question, and how we'll compare is we'll look at that Narendra Modi and Rahul Gandhi both, and it will find that okay, the original reference model has outputted a name of some candidate itself, and so does our policy model or the learning model did. Uh, on basis of that, it will apply some penalty and finalize a new score. If I say R, it will be R minus lambda KL. It will be something like that. I'll give you the exact formula. It is in same derivation. It will provide that okay, if your reward was 1,000, because our reward model is happy because he provided like a Narendra Modi. But KL divergence will be like, okay, you did a good work, but it's not exactly true to give you 100 as a output. I'll give you 80. With the help of 80, we'll add, will calculate some of our loss function, and over the time we'll adjust our parameter. Now, second thing I want to target with the help of this thing only is like now why we need the scale divergence. First of all, what it does is like if I ask another question now, like who is a good actor? Uh, if I just say another question, who is a good actor? My reference model, which was the original model, which don't which is not getting learning over the time with the help of human feedback, will answer Salman Khan, let's say, for right now. But the thing is, my policy model has learned that whenever he says ki Narendra Modi, he'll get a good reward, so he'll again say Narendra Modi as a good actor. Even though, I mean, in terms of acting, we can't just say anything, but to the original knowledge or to the factual information, Narendra Modi is not a actor; he is more a politician. So, but our policy model has learned that whenever he'll say Narendra Modi, he'll get a reward, and he by this he can easily cheat our reward model itself to control that thing and to penalize this behavior. What we'll do is, let's say again this time what our reward model does is it produces some score, let's say 80. Now again two things comes into picture, Narendra Modi plus Salman Khan. What our KL divergence will notice is Salman Khan is from some another category, is from actor category, and Narendra Modi is from politician category. Our learning model is far drifted away from the original reference model now. Why our learning model did this is just to cheat our reward model, just to beat our reward model and get a good score. This will not be like entertained over the time because we don't want just to get a good reward and keep on updating whatever our learning model want is. Now, instead of giving 80 score, we'll put some hefty penalty on this and we'll just give some 10, or even we can go to like a imaginary negative score. Okay, this is not a good answer. And on basis of that, it will update. So when we gave 80, our answer was a positive feedback. Ki, okay, this is a good, like you answered uh, Narendra Modi as a good PM candidate. But when our model answers Narendra Modi as a good actor, like we are very disappointed. Even though he's a politician, you are answering him as a good actor. So this will be our kind of negative feedback which we are providing. And with this, it will calculate a loss function with the help of PPO, and over the time, it will adjust its parameters. So this is how a complete RL cycle works. Uh, I hope now you are clear how this RL cycle works over the time. I'll explain what exactly PPO does is and what its formulation is, but uh, I think this is clear how this exact framework works.
Ankit,
हाँ भैया.
like sorry to interrupt, but मेरे को like is there any library like, which helps you in this, let's say RLHF?
Is there any library?
Library or tool like which is available?
Actually, in this presentation, I'm not covering that
No, I'm just
coding
asking like
part.
out of curiosity.
No, I don't have any actual idea because there are very loose part in this topic. Like, what happens is like people don't also know ki what will be the size of reward model. It depends on whoever is creating. Someone has created reward model of 7 billion and learning model of 70 billion. Someone has took a same thing for all the three model, for reference model, for learning model, for reward model. So there are no hardcore fact ki you
Oh,
this is
acha.
a standard thing that you have to follow. This is more toward a like a
Hmm.
direction to a good fine tuning you can do.
Hmm. Hmm. Right. Okay, fine. Yeah.
Might be I have missed something, but correct me if I am wrong. So ये KL divergence we are calculating for both policy model or reference model. It shouldn't ज़्यादा it shouldn't be get far from reference model, right? जो policy
Yeah,
model का जो output है.
yes,
So
yes.
so like why are we getting like reward model का score KL divergence में pass क्यों कर रहे हैं? Like why this reward model came in between?
I mean, and this is just for a picture ki directly we are passing to KL divergence, but there will be a score and there will be some output from KL divergence which will be passed to PPO. We are not passing to KL divergence. We are just this is for
So
just a flow.
so basically, what is the input to KL divergence?
Okay, for KL divergence, the input will be okay. I think I have we came so far. Like I have a complete line how KL divergence is calculated. Just give me a minute. I'll cover that. So how KL divergence is calculated is again I have explained this thing. It act as a regularization term in reward model. It regularize ki how far your policy model can drift away from the reference model. We'll start with some theory. It's a measure of how one probability distribution diverges from the second. Again, it's the same thing that we did in context with the reference model and the learning model. So there will be initial model that is a reference model that we just studied. And there will be a policy model. This is how the formulation will be. KL diverges DKL. Between the policy model and the initial model is given by like for each here this X is the like token, whatever the token is generated by both the model for the given prompt. This will be the formula how this will work. Like you asked now, how this KL divergence take the input of both the models.
ये so P policy of X क्या है?
It's a probability of a word produced by policy model. The
Okay,
this model.
okay.
This is the mathematical representation of whatever I just told. Actually, this is the formula of KL divergence for two entities. How this thing affect is if I have a reward r theta. If I just go to lower line, this one. If I have a reward r theta, which is the original reward for policy model. I have calculated my KL divergence now. for both policy and reference model. And then I have something, a kind of parameter which is lambda, which will define how harsh we want our KL divergence to affect on our reward. So our final reward, this one R, which we are passing is like a difference of the original reward which our reward model gave. If I go back to diagram and I'll copy this thing with me. So if I just clear out all the junk, so we can see that I get a score which is R theta in our case, R theta. I'll get this P policy from, there will be another arrow, sorry. There will be another arrow here. Sorry for that. This will be output to direct RKL divergence from policy model. The same thing. If I just take it from here, it is the same thing. It will give me P policy, and this reference model will give me P reference. K model, inside K model, or like if I directly don't want, or I'll have some junction, it can be there in this image. But at this point, what I'll get is nu R, which is R theta minus lambda D KL for policy model and reference model. I think it is clear now how this KL divergence works. Pritam bhaiya. Okay.
No, I think see, one thing which is still not answered is the following, that see, you are saying this scale divergence is between P and R, right? P is the generation from the policy model and R is the generation from the reference model. Okay.
Yeah.
Okay, but how exactly this scale divergence is calculated? Because see, the way it is calculated is you find the divergence between two probability distributions.
Yes, sir. So in this formula, there was a probability distribution over each of the token. I will just show here.
So okay, so this policy of X.
It's a probability distribution of a X token of a policy model and X token of a the reference model.
So
this
is X is coming from the policy, or X is coming from the reference one?
This is not a similar same token. This is a two different token, which like if I say, I'll just write here. Our reference model just gave us Salman Khan, and policy model gave us Narendra Modi. So this is this X, this is this X for where X will be X to N. If there is a complete sentence, it will goes to N. So if I go here, this will be probability of Salman Khan log. What our policy model gave is probability of Salman Khan, and below will be probability of Narendra Modi. No, I think this is opposite. Narendra Modi and Salman Khan. This is how this X works.
नहीं, but अलग अलग क्यों रहेगा, सेम रहना चाहिए ना?
अलग अलग रहेगा ना, क्योंकि भैया एक ओवर द टाइम फाइन ट्यून होता जा रहा है। अगर सेम ही रहेगा तो फिर तो हम उसको फीडबैक देने का कुछ फायदा ही नहीं हुआ, if it is answering same thing.
So one more question here. So what is X here?
So X is a tokens in our vocabulary, and right now, like whatever the tokens which are present in those two
So,
different output which are given by these two
so that
models.
is, so see, in case of Narendra Modi, the two tokens are Narendra and Modi.
Yes, yes, sir. Those are
Right.
two different tokens, but I just put right now in.
No, then like the formula will change. See, the
Uh,
probability values are assigned for each token, not for a
yes, yes, sir. Actually, like I just used for reference. This was our complete.
So then, no, maybe you can just change your formula and then you write it for Narendra Modi and for suppose Salman Khan. Then how will this formula change here?
I think, like first of all, there will be some complete line instead of Salman Khan, not just Salman Khan or something like that. In this formula, this will go from X to N. It will work like this only. I understood your point, like if there's a difference between the length of both the prompt. Is that your point, sir? Hello.
Yes, Ankit, you are saying something to me?
Yes, sir. I was pointing कि your concern is like what if there are two different lines, like there will be two different and a set of tokens, like a length of those lines will be different. What will happen in that case, right?
Yes. It is okay if you don't know, just let
Uh,
us know later, right? How
uh,
exactly this KL divergence is calculated?
right now, I don't know like what will happen in that case, but I'll just reply you.
Fine,
So,
fine. Right now, I understand that this is just a kind of a difference between the two generations. Okay, later
yes,
we'll see how to implement it. Okay,
yes, sir.
okay, fine.
So this is how we target our KL divergence. Now, coming to how this PPO works. First of all, where were we? We'll just remove all this. Let's go back to our PPO process, how PPO get updates over the time is. Uh, let's start with function itself, what PPO function is. So again, I think I explained in picture itself that PPO will calculate some kind of loss, and that exact loss is known as clipped loss here, because we are using some kind of clipping function here. This one, I'll explain how this clipping function works. Is let's start with a small entity first. We'll start with what AT is. Uh, I'll not go into deep how AT is calculated, because again this is completely different topic we will be moving, which is about core RLHF. Here I'll tell what AT is, just what AT is. This is a advantage at a time stamp T. Here in our case, it will be more like advantage on token X. What it does is uh, it calculates how much better our response which we have generated now right now is compared to the other responses which could be there, possible responses in the world. So if I say, let's take example, our current responses. Uh, let's go to first question itself. Who is a better candidate for our PM? Let's say its current answer is Narendra Modi. Other answer that could be in that list, there would be other possible answers also. In that line was Rahul Gandhi, or let's say Salman Khan. So what we find is like over these two things, over this Rahul Gandhi, over Rahul Gandhi and Salman Khan, we had a better output right now, and we have an advantage over the other possible outputs which could be there. So this tells us how much advantage we have over the other possible outputs we could have at a given point of time, or in this case at a given position. So this is what advantage tell us. Even in like theoretic, it will be more like same calculating advantage function AT will estimate how much better chosen action or the generated response is compared to average action. If advantage is over 0, it means this action is better than the other action possible at that state. Uh, the state is more in term of traditional RLHF. Will say at that position, that word is how much better compared to other possible words which could be there. So this is what advantage give us. I can't go into formula because then I have to explain what is value function and other things. Coming to second part, this RT. This RT is this RT theta and this is the same thing. What it tells, I'll just start. This is a far simpler formula. I'll tell how does it work. So what it tells is, if I bifurcate this formula is, this is our policy function, first of all, policy model or the learning model. Let's say this is at a after n iteration, or like compared to the past iteration that that model had is policy model at n minus x state or t state something. This is not a reference model, first of all. That thing I'll make clear. So what it tells is this AT is action at time t, and ST is state, at what state we are there at a time t. So what this RT, this complete formula first of all tell is action taken it tells action taken at state t. So what this formula actually state is like our current iteration, or the right now whatever the policy model which have, which might have been improved over the time, its action given at a state t, and like whatever like a copy of a previous policy model which might we have at n minus x step, what action it could have taken at this step. So it's more like let's say this is very simple, like a very layman example. It says that I have a sentence, I am going to now I have to fill current word here. So let's say our pi, this is first, second, third, and this is fourth position. So if I say pi t, our current model, current uh, policy model after n iteration, and previous policy model at n minus x iteration. Let's say it answered, I'm going to, let's say, playground. I'm going to playground. And let's say this answered, I'm going to where. I mean, obviously over the time, if we are fine tuning our model, it will give some better response. So this is more toward like a ratio between like a, what do you say, ratio of playground over where. This is like what exactly this policy ratio means. If I go with wordings, it will be a bit more clear. Policy ratio, uh, probability ratio between policy model and a initial model, old policy, is denoted by this formula. And like this is the probability of taking that action at that given state. And again, like a probability of playground over probability of where. This is this what this ratio is calculating. This is how this thing will go. Like as we see, we can see RT theta denotes the probability ratio between current and old policy. If RT theta is over 1, the action AT at state T is more likely in current policy and if it is between 0 and 1, it is more likely to be the still having some reference of older model. How it will be shown is if I say, just a second, let's say this is probability of playground, probability of wear, and another possible output could be going to here, probability of wear. For sure, this is not a very good output. If I'm going to here, so it would have score between 0 to 1, because still our model is outputting same kind of tokens which it could have generated x steps before. And if I say I'm going to ground, and instead of where, our output is generating a better tokens which will be having a ratio uh, score of a ratio greater than 1, because they state that our model is now having an improvement in these x iterations, the difference of x iteration. So it's more close toward the current policy model instead of the previous policy model. And if a score is again between 0 and 1, it is more close toward the previous policy model itself, and there is no sign of improvement. So this is what ratio means. I think I have went through this ratio. Yeah. If you want to again read, it will be more clear. If r theta is greater than 1, the action AT at state T is more likely in the current policy than the old policy. And if it is between 0 and 1, the action is likely for the current policy, basically less likely for the current policy means it's more close to the older one. So this probability ratio is easy way to estimate the divergence between old and current policy. This is the divergence between old and current policy, not the reference model and the policy model. So be clear with this thing. Coming back to our formula, now we have r theta, a theta, and 1 minus epsilon. Another thing is, what is this epsilon again? 1 minus epsilon or 1 plus epsilon. What this thing says is, let's say epsilon is 0.2. So my range will be 1.2 to 0.8. This will be my range. So it applies that if my ratio, whatever RT theta I have calculated, falls under this range, will accept this clip function with a multiplication of advantage. I'll use some of the color. And this was the original one. Whichever will be the minimum change, minimum difference, we'll go with that, and on basis of that, we'll calculate our loss. So this is the what policy function does, what PPO does. This is how loss is calculated in RLHF. This is all about PPO actually. I think we are done with PPO mathematically. There are few steps which I'll again cover. I hope everyone is clear with what this formula is doing. You can give thumbs up if everyone is fine with this. Okay, so I'll move to wrapping up things with PPO. This is a complete representation of what PPO actually is. Like this was given in paper, I think, or like some famous blogs, like how this thing actually works. Again, this is the same thing which I have drew here. This is more clear. So what happens is I'll have a same prompt. I'll get two output, one from policy model or the learning model, and one from initial model or the reference model. I'll give my output of a policy model to KL divergence as well as reward to get our score. I'll give my this initial model or a reference model output to KL divergence again to calculate how much drifted it is from the initial uh, the from the original production of that model. I'll calculate a new score here with the reward I got and KL divergence, which will be R equal to R theta plus delta D, and not plus, this will be minus delta KL uh, policy model and reference model. This reward I'll take to this PPO, and with the help of PPO, I'll calculate my J theta, which will be loss, and this delta will be the gradient, and I'll change the parameters, original parameters over the time for our policy model. This is how our policy model is going to learn. This is what PPO is all about. If like someone want to know what is the full form of PPO, it is proximal policy optimization. This is only what PPO does, and this is what the complete RLHF, how the complete RLHF works. Should I move to DPO now, because that will be much more easy and it will take very less time if you are familiar with this PPO completely. You can give a thumbs up. Okay. Now, question, if I start with this diagram itself, let's say, because it will be much more easy. What DPO people did is, I'll remove this everything. I'll take some bright color. What DPO people did is, they said, we don't need any kind of reward model because it takes a lot of hyperparameter. We don't want any kind of PPO. And also there is no need for KL divergence. What will happen is, we'll take this initial model, tuned model, their prompt will calculate some loss. And we'll feed it back to policy model. This is all what DPO is about. That's why it is named direct preference optimization, because they skipped all these things, reward model or PPO, everything, tail divergence. This is the basic idea of DPO. I can go deep into formula. Uh, let's start with how this thing works is, like, there would be these two things. If you might have seen nowadays, like even GPT asks which is the more better prompt you want, finds this one or this one, you have to check this is the good one, you can say like that. uh, I'll, this was just initial step how things goes, like for a given prompt there will be two output, and on basis of that we'll optimize our loss function. RLHF and the DPO, the only difference is there is no reward model in DPO. This thing is not there in DPO. There's no LLM trained to receive high feedback. So basically, LLM trains to assign high probability to the positive example. Positive example in the sense this is a positive example, this is a negative example. Low probability to the negative example, and with the help of this, it will calculate its loss, and it will pass it again to this, and there will be just these three steps in
So
DPO.
when you are talking about DPO, so now we don't have any problem with we are moving farther away from initial model, that is reference model.
Uh, they tackled it, but not with the help of KL divergence.
But
If
how?
I
Hmm.
if I just directly scroll down to formula,
It's a function of something.
they use this kind of function where there's a reference also, and the original policy model also. And initially, I shown you two images of GPT producing two output, right? Positive and negative kind of output. This is the W is more like favorable output we want from our model, and L is more like the unfavorable output. So what we want in DPO is just to maximize the probability of response W and minimize the probability of response L. That's what DPO is all about. So this is the loss calculation itself, and beta is the factor how again how much uh, like uh, intrusion we want from reference model. That's what beta does, and sigma is sigmoid function. There will be a simpler image if we just want to wrap it soon. This is what DPO is all about. It will take a prompt. Uh, there will be multiple prompt, positive prompt will also be there, negative prompt will also be there, because we can have a model tuned for good things also, and we want them to learn good things, and we want them to reject bad things, like we don't want it to answer how to make a bomb. So there will be that kind of prompt also, which will help it to learn good thing and bad thing. There's a training model, our policy model. There's a frozen LLM, which is our reference model.
और ये जो लॉस है इन बिटवीन आर पॉलिसी एंड आर रेफरेंस, जो लॉस कैलकुलेट कर रहे हैं इन दोनों के बीच में, ये लॉस कहाँ जा रहा है? ट्रेंड एलएम में जा रहा है कि फ्रोजन एलएम में जा रहा है?
This is going to trained LLM.
ओके.
There's a chosen score, which is basically score is a product of probability associated with the desired response token. So it's more like a probability of whatever words are chosen. It's just a multiplication of that thing. For each word, this is the multiplication of that. My name is Mary. It's a multiplication of that probability. So this is a score, and what rejected score is, it again might have produced two output, like ChatGPT did it earlier. So if I say like a question is, I, what is your name? If my prompt is something like this, what is your name? And if it has answered, my name is Mary, this will be the chosen output. And if it had just answered Mary and just said yours, this is not like a good answer. So it will be the rejected answer, and it will get a score of this rejected answer, which will be the probability of P of Mary into P of yours. So this will be the rejected score. I'll get a result for this reference, and similarly I'll get a result for policy, because it will also produce two output, which will be the chosen one, and which one will be the rejected one. Again, the question will be who decide this, what are the chosen one, what are the rejected one is. These are human based prompts where like these are supervised prompts because there will be some kind of prompt here. What is your name? Something. And it will have two output, which is like chosen and rejected. And it will not be just one, it will be set of these things. If my like model produce something from chosen one, it will be given a tick. And if my model produce something rejected one, it will be uh, declined and will be rejected. On basis of that, I'll produce my this. I got my R policy. I got my R reference. I'll calculate my loss on basis of that, and beta is a factor. Again, kind of parameter.
So a
So
data set so there we would be needing a lot of human resources involved for the creating this data set. Agar data set, if we data set is larger, then the language model would be good, right? So a
yeah,
lot of human resources would be needed for training using DPO.
again, I'll be clear. They have never stated this about how these things are chosen or rejected in paper. They just say that this thing. I'll just picture it. I'll just point it. In essence, the policy, not this one, not this one. Yeah, this one, where YW and YL denotes the preferred and dispreferred completion among Y1 and Y2. These are two different models. Coming to this, YW is the preferred and YL is the unpreferred one. I'm imagining, or like because I read a multiple blog, it must be a scenario they have some kind of data set because they don't have any kind of reward model which is learning all these things explicitly. They have a reward model which is implicit inside policy itself. That is not explicit one. They might have. I'll just point it. In essence, the policy network represent both language model and an implicit reward. The policy network is the policy model or the learning model. It is combination of a language model, the LM, and a reward model itself. So there's no explicit reward model which was there in PPO. It's just about like we keep it feeding the loss and it tries to find which would be the better option itself. So this is what direct preference optimization tells, and this is what DPO is.
So what about the results? Like, is it outperforming PPO?
Yeah, it is outperforming the PPO. I didn't went to results section, but if I show, this is the DPO, yellow dots, and this is our PPO, pink dots.
बहुत ज़्यादा outperform कर रहा है.
So it is outperforming. They use GPT-J also. I think here they has evaluated GPT-4. There were the models. I think they have mentioned which has used these things. I'll just show. I'll just show. I think one of them was, I have written the name here somewhere.
Christopher मैंने presented this paper in AMNL पे, but मुझे कुछ नहीं समझा.
Actually, this was nominated for best paper. There was one very quirky name for that model, Zephyrus. I think it was Zephyrus or something like that. They use this DPO.
Oh, okay. So it is already like अभी भी use हो रहा है.
This is being
used. Okay.
Yeah.
Nice.
I don't have the exact name of that model right now.
Zephyr होगा, Zephyr शायद.
See, this was in addition to DPO, we led servlet approach. Mostly we explore. This was one model, GPT-J, because and one was Pythia. I have never heard name of this model, Pythia. I think Zephyrus was also there. It was done on, I think, PPO or DPO, one of them. So this is all about DPO. Once PPO is clear, DPO is nothing. Like it is very easy. It's more toward the now the paper is full of theorem itself, theoretical analysis of DPO, the theorem one lemma. So this is not what we need. We just want to go with the methodology. I think I have covered that. I think we are over with this.